What's my favourite number tonight?
Possible to pick once again. Run low and want to give again.
Apparently my favourite number tonight is 7, because I'm going to talk about 7 of the most mysterious stars that we've found in the sky in the last kind of 20 years that we've been able to kind of search the sky for planets and other mysterious things. As Dan said, I'm at the University of Bern, I'm a postdoc, and I mostly study exoplanets, but tonight I'm going to talk a bit more about stars and what we do and don't understand about some of these weird ones. So we should probably start with the weirdest star, because we can actually kind of see it, although don't look at it directly. This is the sun. And there's a planet here. I don't know if you can see it. Can anyone point out the planet?
Down.
Yeah, so this was 2 weeks ago. This was the transit of Mercury. And so this is something that, this is what my parents think I study. I look for these things. But what I actually study is this, a blob of pixels on a CCD. So, and the reason is that we can never really resolve and take pictures of other stars. We are limited by just how, even if you had a giant telescope, you can never take a picture of another star. It's so far away and so small. So we have to study stars and planets using just these blob of pixels. And so how do we do that? Well, we look at it in time. So we can stare at a star for a long period of time, and then stars evolve, they change over time, and sometimes this happens. So this is not the transit of Mercury, this is the transit of Venus in 2012. And we don't get to see this on other planets, but what we do see is this on the right. So this is what we call a light curve. This is the flux over time. So you see as the planet passes across the star, it blocks some of that starlight, and it causes what we call a transit. So this dip in light is how we detect planets around other stars. And actually, you see the scale here. So this is in percent. So this blocks only about 0.08% of the starlight. But we can find this around other stars. And it doesn't matter how big they are. Obviously, we can't resolve them. But we can find these kind of planets out as far as we can collect photons from a star. Which is great as well, because it means we can actually do it for multiple stars. So we can do it for tens of thousands of stars in one picture, searching for planets like this. And that is coincidentally how we found about 3,000 of the 4,000 planets we currently know about. So Kepler, which finished a couple of years ago, was famous at doing this. It looked at 150,000 stars. TESS is currently launched, running at MIT, and I'll be going there to work on that. And Cheops is a Swiss mission, which actually only looks at one of these stars, but it uses the same method to study planets. And Plato will launch in the future. And actually, I'm kind of greedy, and I use data from all of these. So you've had a bit of background there. So this is just a little bit more of kind of the toolkit we use when we look at the light curves, this brightness versus time plot we get from stars to figure out what's going on. So this is a planet. You see the depth again is about less than 1% usually. It's kind of U-shaped. This is where it's entering the star and then crossing the star and then leaving the star again. And it lasts a few hours. So this is about 0.1 days down the bottom. And the depth gives us the planet size. So bigger planets block more light, and we get a bigger dip. And something else we can get, this is kind of a longer time frame here. This is 20, 30 days here. You can see here multiple dips, and obviously the planet on its year's orbit will cross the same part of its orbit every year. And so the distance between these dips tells us the year of the planet. And also you can get multiple planets crossing the same star. So there we have 2 planets in different orbits with different sizes. And that's how we find planets. But we found like 3,000 of these, and these are kind of boring. These aren't the weird things, and I'm tonight going to talk about the weird things. But there's some other things we should know about first. So stars aren't just spherical blobs. They do have their own things going on. They have stellar variability, which happens. This tends to be from star spots, like we have on our sun. But it causes variability over longer time scales. So here you see this is in these dips are like 2 or 3 days at a time. So these are different from the transits that planets cause. And there's also, so not only planets orbit stars, sometimes stars orbit stars. A lot of stars are in double or triple systems, and these cause eclipses. And we call these eclipsing binaries, and they're a lot deeper. So you see here, this is a 25% depth. So it blocks a lot more of the light of the star, because stars are obviously a lot bigger than planets. So that's kind of our toolkit to go into what we've found and what we don't understand about some of these stars. So we'll start with this one. So this is, it's off the top. Oh, well. This is, we have, as you'll see here, astronomers are terrible at naming things, right? So most of the time, these are star catalogues. There's 1 million stars in that catalogue. We take we find one and we name it after whatever number it is, right, in that catalogue. And so this one, you don't need to know, but it's kick 285 something. So what do we think this is? I just showed you a few light curves of things that we understand. So who thinks this is a planet? Show of hands. Okay, a few people. Who thinks it's a eclipsing binary? So a star going around another star. Okay, a few more. And who thinks this is something completely different? Okay, so this is in fact a binary. So you might be able to see here, this is very V-shaped. It tends to be the V-shaped eclipses that we see are stars because are binary stars crossing other stars basically. And you don't, because for a planet you usually have this very nice U shape. But what happens that's really interesting is that we have this normal binary going along with these V-shaped eclipses. And then randomly you get this thing that happens. And this is unlike any other eclipse ever seen. So this is seen by the Kepler spacecraft, and it observed 150,000 stars, and this is probably one of the weirdest things that was spotted. So what the hell is going on here? And the weird thing as well is it happened more than once. So this thing happens 7 times during the Kepler mission, and it's very regular as well. So that tells us something's happening, right? And it's probably an orbit of something. There's something going around something else with this orbit, and it's blocking the starlight in a weird amount every 200 days. And it turns out it looks kind of like there's 2 stars that are crossing in front of another star in the background. And every time one of these stars crosses, it blocks some light of this background star, it causes one of these weird dips. And this seems like it would be a logical thing, and in fact this system is called the impossible triple system, because it is probably 3 stars that are causing most of the kind of the light curve we see, but if you try and model it with 3 stars, this is what you get. So the blue line here is if you have like physics turned on, like what we'd expect from a normal triple system. This is what you get. You don't match it at all. You can't make it work. You can try it any way you want, and you can't make 3 stars cause this eclipse. What you can do though is if you can turn off Keplerian orbits, right? So Kepler found out that planets and stars orbit in a certain velocity, they orbit at a certain distance given their period, right? This is like fundamental physics. You can't just turn it off. But you can when you're doing simulations, and it fits, right? This is weird. This should not work. And it turns out that why it fits is because you need these stars to be going faster than they currently are, given normal physics. And the only way to do that is to add some extra unphysical star that you don't see, but it's there, and it's causing the 2 stars that are crossing the other star to kind of speed up during their passage. And you also require it to be on this period. That means that every time, so these 3 stars, for example, are going all the way around this background star every 200 days, and every time it crosses in front of that background star, it's at the same position on its orbit. So you need a 0.1% precision on the period that matches up with that. And it's a crazy, crazy coincidence, but that's probably the likely thing, unless maybe there's something else going on. But for the moment, we can't really explain this. We don't have enough data to say what's actually causing these weird eclipses, but some sort of like massive star, maybe a black hole, maybe a neutron star, maybe a white dwarf, that's kind of mysterious, that's there, that's pulling these stars around a bit faster, seems to be the best way to do it. Okay, so we played this game before. Who thinks this is WD 1145, is a planet? Any hands up? No one, okay. Understandable, it's got this V shape again. Okay, who thinks this is a binary, a star going around a star? Okay, we've got a few hands. If you said binary, then you're saying exactly the same as the Kepler pipeline said when they found this star. They saw this V shape, and they said, okay, it's probably a binary. But the WD in the WD 1145, which is cut off at the top, is important because that stands for white dwarf. And a white dwarf is an extremely tiny star. And so this changes everything, because a white dwarf is actually the size of the Earth. So if you have an Earth going around a white dwarf, it would cause an eclipse like a star would. So actually, this means that whatever is causing these eclipses is far more likely to be kind of planet-sized or smaller, right? And another thing to keep note of is that normally when things orbit stars, they orbit at the same period. You know, a planet goes around at the same period. But when you look at this star, you see multiple periods, which doesn't quite make sense. So you see these are peaks in period space. It looks like there's something going around at 4.6 days, something at 4.5 hours, sorry. And they have different eclipses. And then, so what you can do is you can go look at it in higher resolution. So a bit like the orbital motion blur you get when you're looking at something moving very fast. In order to actually see what's happening, you need to look at it at higher exposure time, right? You need to do it in high speed, effectively. And when you do that, you see that these dips are actually masking some weird behavior that's going on under there. So these are 10-minute eclipses which are happening. And there's these strange dips that are like asymmetric, and there's a ton of stuff going on here, right? So these are minutes on the top. So it looks like there's hundreds of objects that are causing these dips. And they're in no way a star or a planet that looks like it could do this. So what the hell is going on, again? Another thing that looks like it's happening is that if you look at the star for periods of 4 hours at a time, it seems like some of these dips move. So every orbit, rather than staying on the same orbit, they shift. And some of them drift away as well. So what this all seems to point to, and it fits with all the evidence, is that there's a hidden planet, or dwarf planet potentially, near the star, and close enough that it's being tidally distorted, and some of this material is being thrown off into an orbit around the star which is blocking what we're seeing. And these little asteroids that are getting thrown off, they are giving out dust which is blocking the starlight. And actually I put this on our list even though this is pretty well explained now. I think it's pretty confident now that this is indeed what's causing these strange dips we see around WD 1145. Okay, right, 5 more to go, sorry. Number 3 is this thing. So this is another strange looking dip. So this was actually not observed from space. This was a telescopes that looked from the ground. And the reason they were able to do this is you need to note the scale. So this is the light coming from the star. So 100%. So normally at the start it's not doing anything. And then the star gets almost completely covered. And for a period of, this is 50 days here. So for almost a month the star is almost completely covered. And when Eric Marmajek first found this, it's also named after him, this star. I'm pretty sure, like all of these light curves, it was probably a what the fuck moment, right? And there's also these strange variations going on in the eclipse as well. So what could be happening here? One thing to note about this star, like astronomers don't care normally where a star is on the sky or what constellation it's in. I could name about 4 constellations, but it's important to note where this star is because it's in the Centaurus constellation, and that has young stars in. There's a cluster of young stars which are all about 100 million years old, and young stars have dust. So this is, as we saw earlier actually, this is a radio picture of a protoplanetary disk. So planets are forming in this disk, and it's forming from the dust that goes around the star. And when there's dust in a system, it can have these weird effects. It can throw up these dust storms above the plane of the disk that block the sunlight and cause dips like we maybe saw. So what you want to do is look for the starlight in the infrared, because these disks, just like Earth, just like humans, we glow in the infrared. We're at the right temperature where, unlike stars, which glow in the optical, we glow in this this light further than red. So if you look for light in that range, and there's light there, that tells you there's dust there, that tells you there's dust causing these dips. And when you look at Marmajek's star, you don't see anything. This is what the star should look like normally, and then if you should see any dust there, you would see a bump, but you see nothing. You see that there's clearly no dust in the system, at least around the star, not enough to cause any sort of effect that we would be able to observe. So what could be going on? Well, what if the dust isn't actually just around the star? What if there's some smaller region of dust there that's collecting for some reason that's causing this eclipse? And that's the leading theory for this star, in fact. So let me show you what the current best guess for this this light curve is. So here we have the star, and we're looking through something at the star. And this is a disk around what is thought to be a giant planet, in fact, that's orbiting the star. And then you have these gaps in the disk where exomoons, so moons are forming around this Jupiter. And these explain these gradients we see in the light curve. And this explains, actually, for an astronomical model, this explains the data amazingly well.
Yeah.
Trust me on that. But it does have a few problems. The main problem is that actually using that model, you can predict where this disk is in the orbit around its star, and you can predict how big it is. And it turns out it should be about 1 AU away from its star, and also about 0.5 AU across. And that doesn't really work. If you have something that big, it should be being disrupted by the star, right? I mean, and also if it's on a 1-year orbit, so a 1 AU away, so that's the distance between Earth and Sun, it should come around every year. And we've not seen it. We've been looking for 15 years, and we've only seen this happen once for this star. So that might mean it's on an eccentric orbit, like a comet, where it comes in and it eclipses the star and goes out again. But again, this shouldn't be a stable configuration. So quite how this is stable, or if it is indeed a dust ring, is not yet known. But it's one of the most interesting systems in the sky. And we're hoping to see another of those eclipses. Okay, so this next one's a bit personal for me, because I was basically looking for another one of these, and I found this. This is also in the ground-based data, and this is PDS 110, and it looks maybe like another copy of that J1407. And I asked my friend who runs or is involved with another survey in the States, and if he had data on this star, and he said, yeah, we've got this. And I was like, great, it's confirmed. And then I realized, actually, wait, 2008, 2011, we have a repeating eclipse here. So we looked for when the next one would be. We predicted it to be 2017, and we went and got data, and we were like, right, we're going to confirm this. It's going to be a ring system. It's going to be amazing, and it was a flat line. So what a waste of 50 people's telescope time, really. But and we should have really known better, because when you look in the infrared, it has this huge disk. So there's dust in the system, and the dust is just being blown off the disk and eclipsing its star. So we, put a nail in that coffin. But it's still unknown quite how these dust disks can cause these eclipses. But it's less weird than J1407. Anyway. Moving swiftly on to number 5. I've lost count as well. Sorry. So this is what I call the shark tooth. This is a star from K2. So you see. You can see the weird eclipse here, and this could be a binary, right? So this could be just one of these deep eclipses that I showed you at the start. But actually, when you look at it up close, it has this very asymmetric shape. Whereas all of the stars and planets and everything that's massive in the universe is a sphere, because gravity pulls things into spheres. But this can't be a sphere. If it's this asymmetric, there must be something else going on. So I was the referee of this paper, and when I got this paper, they said this was the best model. It was some strange skirt was crossing the star, and they did this fit. And then I was like, because I was obviously working on this thing, and I was like, this looks like a disk to me. And so I sent them an animated GIF in my review, and I said, have you tried this? And it works way better. So I think I found this, really. I mean, they missed a trick with this, I think. But once again, so it looks really like a disk. This model works great again, but there's still more problems with it because, we don't have a second one, so we can't confirm it. And also, once again, we have enough time span on this star that we should be able to see another one, given how fast we expect it to be going. But we don't. So that means it might be on an eccentric orbit. Or maybe something else is going on. Maybe it's not a disk at all. Maybe, weirdly, it's in the same part of the sky as J1407. So maybe there's some connection between these two, but nobody's been able to work that out yet. Okay. So, number 6. this is one of my favourite stars. This is the weirdest star probably found by Kepler. So this is KIC 846, or Boyajan's, or Tabby star, it's known as. So you see most of this is a 4-year light curve, so this was observed by Kepler for 4 years. Most of this timescale, it's not doing anything. It's just a normal star, some variability, but not out of the realms of possibility. And then, well, at the end it goes crazy. And then there's a couple of other places in the middle where it's also doing some strange things. And these are those dips zoomed in. So you see these asymmetric, weird dips that you can't explain with anything like a planet or an eclipse. There must be some sort of structure there, some sort of asymmetric dust going on, possibly. So once again, you can do the same trick. You can say, okay, if there's dust here, where is the dust? Can we see it in the infrared? And you go and you say you find nothing. Once again, you find none of these bumps. So there's no dust disk around the star. There's even probably not a large asteroid belt. We can put the limit on that. So what kind of happened after this got published is the media went a bit mental. And I apologise, as an English person, we have the worst newspapers in the world. The Daily Mail just publishes such nonsense on a daily basis. And so they said, okay, it's a megastructure, it's a Dyson sphere, we found aliens. No. But we should probably look at this theory in a little bit more detail and pick apart why some people might say that. So could it be aliens? So a Dyson sphere, I don't know if you've heard of this from sci-fi, but a Dyson sphere is basically where you try to use all of the energy from your host star by covering it in solar panels. So you basically build a giant solar panel around 360 degrees of your star in order to harvest energy from it. But the problem with this is that if you're going to do this, you're basically going to build a warm metal disk, or warm metal sphere around your star. And it's going to be warm, it's going to glow in the infrared. So in fact, we already ruled this out before the paper was published. And in fact, even the paper by Jason Wright, which suggested ways to find alien megastructures, it said this star is not one of those examples. And also, it predicts another thing, which is that, okay, if you have a large structure crossing the star, you should just block starlight. Whereas if you have dust crossing the star, the dust actually refracts the starlight, like a sunset. So it should predict that the eclipses are the same in every colour. And it's been eclipsing since it was discovered, and so we can go and test that. And it turns out that it's basically, there's more light missing in blue than there is in red, which means that there's dust. It means that there's no structure around the star. So we can effectively say there's no aliens there, unless the aliens are building their Dyson sphere out of dust particles, which is very unlikely. What it looks like it might be is some sort of comet swarm, or maybe an asteroid collision in the system which throws up dust on a very kind of short time scale, but probably not aliens. So, glad you're still with me. We're on to the final star. And that is, again, a horrible number, EPIC 2497, or the random transitor. So, we can play the same game again. Like, who thinks that this light curve, I can even zoom in, this light curve comes from a planet? No guesses. Okay, one or two half hands. Who thinks that this is a star, like a binary system? Who thinks that this is something else? Okay. Who thinks that we don't have any fucking idea what this is? Yes. You people are correct, because we don't know what this is. This looks like a planet. Okay, if I zoom in on the eclipses, the transits, the things, the dips, this on the bottom is what the dips look like, and this on the top is just a planetary system for reference, right? These look like planetary dips. These are kind of flat bottoms. They've got some noise going on, but they kind of look like planets. But the problem is, planets are periodic. And so what we do normally with these systems is we run a periodic search, and we find huge peaks at the period of the planet, because every single transit lines up. And when you run the same thing for HD 139139, you get noise. There's literally no period to be found in the entire light curve. And also, if you look at the position of the transits, and so this red line here is what you would expect if you were picking transits out of a hat. at the times that, at whatever times you thought were, necessary, I don't know. And then these dots are the transit times of the system. So these transits, even though they look like real transits, they're basically the same as random selection. So that we have no idea what is going on here. So the best thing to do, as with all these cases, is to try and get more information and to try and make some hypotheses. What could this be? So the first is maybe there's. Oh no, this is mine. Oh, that's fine. Maybe there's a ton of planets, right? So maybe every single one of those dips, and there's 26 in total, is related to a different planet. But the problem is each one of those dips, they're all the same size, they all have almost the same depth, and they have these durations, so you can tell from the duration of the transit how long the period is, and all the durations suggest they're really short period objects, that whatever is eclipsing the star is very close to it. And so you can basically rule this out because the likelihood is that you can't make this work. Certainly that it would be very unlikely to find 20 planets that transit that all happen to give these strange signals and are stable as well, because if you have 20 planets in a system close to its star, it's not going to be a stable system. So we can basically rule planets out. So maybe it's like a disintegrating planet. Sometimes we have these where we see some transits turn on when the planet throws out dust and then they turn off again. But also this should give some sort of periodic signal, and we don't see any periodic signal at all. Similarly for asteroids, there should be a periodic signal where the bulk of the asteroid is orbiting the body and we don't see anything. Possibly in a binary system, if you have a planet going around a binary, sometimes it eclipses their stars, and sometimes the stars have moved because they're orbiting each other, so you don't get an eclipse. But the problem is that there's so many dips, and they're on such short periods that you shouldn't have a binary system short period enough in order to cause these dips. So this shouldn't be a possibility. Quadruple star system is kind of my best guess for this system, and I think if I worked at it for a year, I could get a decent model for it, because there you have two stars which are orbiting each other in the background, and two stars which are orbiting each other in the foreground, and sometimes they cross and give you a transit, and sometimes they don't. And you can make it work so that they don't give you any periodic signal, even though there's a real kind of effect going on there. Possibly we have dust around it, but actually we can rule this out again because we don't have any infrared in the system. So there's no hint of dust around this system. And possibly there's some stellar variability going on that we've never seen before, but it would have to be the only star in a million to have some strange stellar variability of this kind of effect. So could it be aliens? I mean, it sounds like a ridiculous thing to ask, and astronomers won't ask it unless they're presented with a system so weird that it forces you to think of the improbable things. And neither of these kind of options seem likely. So I think, although we should consider every option, you have to weigh them by the probability of what's likely to be happening and why is this signal. In the case of aliens, we have to consider why would an alien do this, and maybe an alien is doing it just to mess with us, right? Because we can't explain this otherwise. But I think it's more likely that that there's some physical reason for the star, and that we'll eventually find out a model that can explain it. But I think we have to really think about Arthur Conan Doyle's quote here, when once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. And I think if we are going to find aliens, that's going to be how it will work. There will be people that we'll have to eliminate every single hypothesis until we settle on that one. And so I hope I've given you a little taste of some of the stars which we don't understand, where we've gone through this kind of eliminating the impossible scenario. And I hope as well I haven't left you with the impression that we have found aliens, because we 100% have not, and we probably will not with this technique. But I'll leave you with that, and I'll I said I had a podcast, so I'll sell it here as well. So yeah, thank you very much.